Okay, thank you. And firstly, thanks to the organizers for the invite. I'm very happy to be at this very enjoyable meeting. I'm going to give, as is my style, a very non-technical, elementary talk, mostly giving a kind of survey of an area I find very interesting. I'm not going to cram this with content. Hopefully the stuff I do tell you about will be understandable. And I appreciate it very much if you interrupt me at any point and ask me questions if anything's unclear. This is meant to be understandable to non-experts, so raise your hand at any time. So we're going to talk about the Aviles-Giga functional. This is the Aviles-Giga functional here. Quite a simple functional. And we're minimizing it over the space of functions that are up here. W22, it's 0 on the boundary. And we insist that it has the gradient equal to the inward pointing unit normal. So here is our domain. Here we've got the inward pointing unit normal to the boundary. We have something which is 0 around the boundary, and the gradient is equal to the inward pointing unit normal. So how do we think of this? Imagine we painted this table here. And we put a kind of heat lamp underneath the table, so it heats up this thing I've just drawn. So the heat is going to force the paint to kind of blister off, to lift off the table here. Okay? Around the outside where it's not heated up, it's still going to have 0 boundary condition, and the gradient equal to the inward pointing unit normal we can't explain. So we just have that for some other reason. So that's what this thing is designed to capture. It's a model for blistering. It's a model for a whole bunch of other things. There's a very closely related functional called the micromagnetics functional, which is about magnetizing thin.
Sorry. So, I mean, you suppose the gradient to be the normal or just this condition, this color product condition which you write there?
I assume it's the normal, so that's a more general condition, but let's say it's the normal. So if you take a thin magnetized film, then the magnetization will be given by a vector field, and what kind of magnetization patterns you can get is modeled by a close cousin of this functional. So that's the guy we're going to be studying. And like any minimization problem, our first job is to try and get some idea what kind of thing is going to lower the energy. So let's take a ball. Let's take a ball as our domain. A natural candidate would be the distance function away from the boundary, as I've drawn here. So if we take the distance function away from the boundary, for sure it's got 0 boundary data. The gradient's equal to the inward pointing unit normal, no problem. The only problem is that the distance function away from the boundary is not in W22. We have a jump in the gradient at the center, right? So what can we do? We convolve it. So we have all these guys here pointing the way we want, and we have some kind of singularity right here. So convolution, for the purpose of this talk, is just taking the average on a small ball, which morally is exactly that anyway. So if we take the average over a small ball, right in the center we have something whose gradient is 0, and around here we have something whose gradient is small. So around this region where we're intersecting the singularity, we'll have that the gradients are smaller, right? So that's going to contribute to the energy, because the energy is forcing us to have gradient close to norm 1, okay? So the kind of energy of the functional is being focused here on the center, and around the outside the gradient's got norm 1. It's oscillating a bit, but not too much, so we don't have too much energy here, but it's really where we have the jump in the gradient that the energy is concentrating. Okay? So that's one candidate domain. Let's take another. Let's take the rectangle. Same thing. Let's take the distance away from the boundary. If we do so, we get a Lipschitz function. And the gradients are pointing inwards like this, and across these interfaces here, where the points are equally close to one boundary or another, we've got a jump in the gradient. Yeah? So we're going to do the convolution, and when we do the convolution, anywhere inside this, it's just a constant gradient, nothing changes. When the convolution kernel, which is just the average on a ball, intersects this boundary, we're going to take the average of 2 gradients, which are both vectors of length 1, okay, with different angles, and the average of the 2 of them was going to be some vector of length strictly less than 1. Yeah? So around these regions where this ball, convolution kernel of size epsilon, intersects the jump in the gradient, we're going to get the energy concentrating. Yeah? And when it's here, when jumping from one gradient to the opposite one, then it's going to be 0 gradient along here. Yeah? So again, we see that the energy is concentrating along the jump in the gradient. And the finer convolution kernel we take, the more the energy is going to concentrate. Okay, so that's a rectangle. Let's do an ellipse. That's not an ellipse. Let's do a stadium. Okay, so we've got gradients pointing inwards all the way around. Okay, and the same thing. Along the central line here, we have a jump in the gradient. When we do the convolution, we're going to get a whole bunch of points whose norm of the gradient is strictly less than 1 or equals 0 right in the center. Again, the energy is concentrating here. So it looks like what we've got is some kind of thing that is picking up the jump in the gradient as the energy of the functional. Okay, so this thing is a higher order version of a well-known function which we've already seen today a few times, which is the Motorola functional. So I'm going to very briefly tell you again about the Motorola functional. So the Motorola functional, we've got u going from some region omega into r. We have something like this, 1 minus u squared over epsilon. Maybe we put a 2 here, but we can rescale and get rid of it. But OK, let's put a 2. And if we want to produce something non-trivial, let's have the integral is equal to 0. So it's like a kind of model for oil and water. This thing is forcing it to have values either plus or minus 1. And this thing is kind of constraining the oscillation. So a typical trick is this a squared b squared is big and equal to 2ab. So then if we do this with these coefficients, we have that this thing, let's call that m epsilon of u. We have that m epsilon of u is greater than or equal to 2 times the integral of 1 minus u squared gradient of u. Okay? Can you see this? So this is our domain. And we have half of this being roughly plus 1, and half of it being minus 1. And as we take a sequence of un such that the energy is finite, okay, so let me put that somewhere else. I forgot the eraser. So if we have epsilon n goes to 0, and we have un belonging to w12 integral is equal to 0, such that Motorola energy is less than infinity, that means that this expression is uniformly bounded. Okay? So when we have the jump from plus 1 to minus 1, this thing is of order 1, right? And that is where the action of the function is going to be. That's what it's. The only thing it really wants to do is to jump from plus 1 to minus 1. And when it does so, this is of order 1. And this thing is just the L1 norm of the gradient. Yeah? So this is not as good as having the L1 norm of the gradient is uniformly bounded, but morally it's not a million miles away. And if we did just have that the L1 norm of the gradient was bounded, we know the limit would be in BV. Yeah? So let's pretend we can avoid these technicalities, which are not hard. It's just a little trick. So we can kind of, so this is my symbol for kind of being able to deduce that L1 norm of the gradient is uniformly bounded. Then the fact that the Motorola energy is bounded means that the limiting functions will take either values plus or minus 1, okay? And the limiting functions will be in BV. So we'll have a limiting function space. We'll have a limiting function space of functions w belonging to BV such that the integral of w is 0, and w of x belongs to +1, -1. And since the energy which we were looking at was approximated from below by this expression, and I claim this is somewhat like just the L1 norm of the gradient, then in the limit, this is kind of like having just the BV norm of this W, which will just be the H. Well, it'll actually be an SBV, and it'll turn out to be just the H n-1 measure of the jump set of W intersect our region. Okay? So our energy looks more and more like, in the limit, just the jump, the H1 measure of the jump interface. And this can be done in a very rigorous way with this notion of gamma convergence, which I don't want to go into technicalities of, but gamma convergence is the most natural way to extract the limiting minimization problems from a sequence of parameterized problems. Yeah? And for, it's gone, but for epsilon, we have a sequence of parameterized problems given by this thing. Oops, there's an epsilon here. And the limiting problem is just the minimization of the jump set over the space of functions that takes values +or -1, which is in BV. Okay? All that stuff is perfectly nice and natural, and to prove it rigorously is I think it's the first non-trivial or really non-trivial example of gamma convergence, and it was a big achievement by Motorola in the 70s, and it's a very nice theorem. So what we were doing is exactly the higher order version of that. Instead of having u, scalar valued function, and the derivative of u, we have gradient of some function, second gradient. Exactly higher order. Go ahead. Yes. So the Aviles-Giga functional is this thing. So it's just one gradient up. Yeah? It's also the Ginzburg-Landau applied to gradient vector fields, if you want to think about it this way. Okay? So what we'd like to do is to understand the gamma limit of this sequence of parameterized minimization problems. And from the examples we studied, it seems like the energy is concentrating on these jump sets where the gradient's jumping, just like for the monochrome Motorola, the energy is concentrating exactly where the function jumps from +1 to -1. So by analogy to monochrome Motorola, we'd expect kind of a neat theory to be available to us to extract the limit. Yeah? So we would guess that the limiting functions are such that the gradient belongs to SBV, right? So we're one gradient up. We're now doing this for gradient vector fields. So we expect the limit to be such that the gradient belongs to BV now, yeah? Or SBV. In the limit, we'd expect the norm of the gradient to be equal to 1 everywhere. So we'd guess the limiting function space would be something like this. Yeah? And by analogy, we'd also expect to be just picking up the jump in the gradient, because that's what we saw from examples. Everybody happy with this so far? Huh? Making sense, yeah? For some of you, this is very elementary, so apologies for this warm-up. So that's what we might expect. And the reason this subject is so interesting is that this is not true. So let me go to this example. So let's take, so I'm going to draw this anyways. I give you pictures in case my drawings are incomprehensible, but I'd rather draw it also. So suppose we have a domain, looks like this, and we have gradients pointing inwards like this, and pointing inwards like this. Okay? And we're going to try and understand what happens when we convolve this distance function away from the boundary. So again, convolution is morally just the same as taking average over a ball of size epsilon. So let's take a point here, call that point A, and a point here, call that point B, which is, say, epsilon away. Let's make them a bit more. Say 2 epsilon away from this interface. So let's average over a ball of size epsilon, and then let's move this ball from A to B, and let's see what happens to this expression for the energy we get from doing this geometric sum inequality. Let's see what happens to this thing. Let me do that again. Where u epsilon is u convolved with convolution kernel of size epsilon. Okay, so let's do this integral across this line from A to B and see what happens to the energy. Okay, so let me see if I can move this thing up. Is this like this? Ha, all right. So what happens to energy? Let's break up the expression into two pieces. Let's consider this part first, 1 minus gradient u epsilon squared. So here is our interface. Okay, here we've got gradients pointing like this. Here we've got gradients pointing like this. We're moving across like this. Okay. So when we're at A, we're taking the average of this gradient. It's just the same thing. Nothing happens, right? Same thing on B. Nothing happens. So this thing is equal to 0, both at A and at B, right? What's the worst thing that can happen? It's exactly smack in the center, right? And if it's smack in the center, what are we doing? We are averaging these guys with these guys, yeah? So let's draw a bigger picture of that. So we've got some vector like this, of length 1, and some vector like this, of length 1. Let's make the assumption that the angle on both sides is theta. Okay. So I'm tempted to ask you what the length of the vector is, but I don't have the courage, so I'm going to just tell you. It's going to be this length here, right? And the length of this thing is just going to be what we get from trigonometry. It's just going to be cosine of theta, right? Yeah? Cosine of theta. So that's going to be, if I had a different color, I think I do have. There we go. This vector in orange is the average of the two vectors, and it's got length cosine of theta. Yeah? So that's the worst this can possibly be. So if we put it inside this expression, we get 1 minus cosine squared of theta, okay, which is like sine squared of theta. So the biggest this expression can possibly be is sine squared of theta, right? So this expression here will go from being 0 to getting to be sine squared of theta and then back to 0 again. Yeah? So let's try and draw a graph of this thing. Let's put it here. So at minus 2 epsilon, we're 0. At 2 epsilon, we're 0. We go up to a height of sine squared theta, and then we go down again. So that's the graph of 1. That's the graph of 1 minus gradient epsilon squared, and this thing is sine squared theta. Okay? So that's one part of the expression. Let's do the other part of the expression. Let's consider what happens to the second gradient as we move from A to B. We've got a very similar picture, right? We're going from this vector to this vector, or this vector to this vector, if you go from left to right. And then, so what's going to happen? Let's make this looking the same. We're going to do a jump from this vector to this vector. Yeah? And the angle is theta. So, anybody want to volunteer how big a jump we're going to make? How big a jump is that? It's going to be just this distance, which is 2 sine theta. Huh? It's going to be 2 sine theta. Yeah? So what's the norm of the, what's the graph of the second gradient? Well, it's not changing as we're here, okay? And we move along. And then we do this transformation, we get to there. So it goes up like this, very high, and then goes down, right? And the entire integral of this second gradient from A to B is like 2 sine theta. Let me put it down here. So the actual energy we're interested in, which is the product of these two expressions, okay, it's kind of like this graph multiplied by sine squared theta, roughly. Yeah? So if we take this graph and multiply it by sine squared theta, then the L1 integral of that function will be sine to the power 3. Yeah? Just rough arguments. Huh? So what we've got is that the integral from A to B of 1 minus gradient u epsilon squared, second gradient of u epsilon, along the line from A to B is of order, let's say 2 sine to the power 3 theta. And for small theta, this is like 2 theta to the power 3. Yeah? Wow, that's very important. That's very important because that means what we hoped was true is absolutely false. So this is a picture of our two graphs again, in case those pictures don't make sense. What we hoped was true again was that as we took a sequence of functions of bounded Aviles-Giga energy for some sequence epsilon n going down to 0, we hoped that the gradient would be inside SPV, right? And we also hoped that the energy would just be the jump in the gradient. We've just learned that the energy is not the jump in the gradient. It's the jump in the gradient to the power 3. So on this example here, as we integrate the energy from A to B, we get a jump to the power 3. Yeah? So straight away, that kills BV, right? Because we can easily cook up an example where we have these little fine angle jumps, where we sum the angle jumps to the power 3, it's finite. But when we sum the angle jumps to the power 1, it's infinite. So we can construct a sequence of bounded Aviles-Giga energy whose BV norm is going to blow up. It's going to have perfectly good bounded Aviles-Giga energy. So we're not going to have a limiting function space whose gradient's inside BV. That's dead. No hope of that anymore. And second thing we know is that we're not just counting jumps to the power 1, we're counting jumps to the power 3. And actually jumps to the power 3 has been observed physically in micromagnetics for a long time. It's one of the very nice things about this subject is a lot of these physical laws which have been seen are recovered somewhat naturally from the mathematics of setting up these models. So the two nice things that would make this whole story very simple are totally false. So here's a little summary. I don't know how well you can see this. This picture I've taken from a paper of Ambrosio Delelis-Mantegazza, which are the foundational papers of this subject. They construct this domain by doing these kind of crinkling origami type things. So we have a scalar function where we have these jumps inwards and outwards, and we make them more and more fine. And we can easily make the jumps to the power 3 finite and the jumps to the power 1 infinite. So you just keep doing that with finer and finer crinkles. The limiting function will not be in BV. Yeah? OK, so no hope to be in BV. How do we go further? OK, so now we have to do a little bit of calculation. I promise we will not go too deeply into technicalities, but we need to calculate sometimes, and this is one of the times. So let's suppose we have a function in W22. And I've cooked up these funny expressions that look really weird, but just bear with me for a bit. Let's just create this vector field from first order partial gradients. Okay, first order partial derivatives of our function. And let's create this vector field here. Okay? It just happens that when we take the divergence of this, we'll get some cancellation and we'll get exactly this expression out. It's a 1-minute calculation, check for yourself. Okay? Just happens to be true. And now let's cook up another vector field made up of first order gradients. And again, it's going to be a vector field whose coordinates are third order polynomials, this guy. Okay, let's cook up this guy. Again, little calculation, take the divergence of this guy, you get some cancellation, you get this expression. Yeah? And this expression is an expression which we can bound by our energy, this thing. 1 minus gradient squared, normal to the second gradient. Yeah? And the same is true of this thing. Okay? These calculations are from a paper of Jin and Cohn. Let's keep that for a second. What can we do with that? This is my most technical slide. I promise it gets easier after this. So let's take a sequence of functions whose Aviles-Giga energy is bounded. Okay? Now let's suppose, and it happens to be true, that we could prove that this sequence converges strongly in W13 to some limiting function. That's highly non-trivial. That's a big theorem. That's the so-called coercivity part of gamma convergence. And there's nothing about the natural initial situation that you could hope makes that obvious, because all you've got is this thing is bounded for your sequence, okay? And as the gradient gets closer and closer to norm 1, you have weaker and weaker control on the L1 norm of the second gradient. So there's no obvious reason why you're going to get compactness of the gradients, but you do. Let's assume that's given. So the gradients converge strongly in W13. If we knew that, then let's take the limiting function u, and then let's create a linear functional out of it. So take our linear functional defined by taking some test function of compact support phi, and let's take the expression here. We'll take the gradient of phi dot product, this crazy divergence, this crazy vector field we created from first order partial gradients of our limiting function u. Okay, let's do that. Since we've got convergence in W13, the first line is equal to the limit of the second line as we approximate our function u with the sequence un. You have strong convergence of gradients in W13, so that's definitely true. Yeah? But once we're talking about our sequence is in W22. It's in W22. So we can actually integrate by parts, and it's got compact support, so we're just going to get this nice expression. This is just the divergence calculation that we did before. Huh? Yeah? And cool, because this thing is uniformly bounded by our energy. So we have this thing is less than the L infinity norm of our test function times our energy. So we've got that this is a bounded linear functional. Huh? This is a nice bounded linear functional, just from our calculation from the page before. Since it's a bounded linear functional, it's a measure. It's a measure mu, which depends on a function u. Yeah? Okay. And we can do the same thing with the other. That's actually an advantage. Keep them both on the same page. We can do the same thing with the other guy. Okay? So we have these two measures, mu depending on u and nu depending on u. Okay? And it turns out these guys are going to play the role that we would have liked to have had if it happened that our gradient was in BV. If our gradient was in BV, the gradient of the gradient would be a measure, which is not true. But if we cook up these completely crazy vector fields made up of first order partial gradients, okay, and then take the divergence, turns out that thing is a measure. Yeah? For our two choice of divergence, for our two choice of gradient of vector fields. So once again, we can't use the theory of BV functions. That's kicked out. So we're going to try and get a substitute for that. So instead of talking about the gradient of the gradient being in space of measures, we're going to create some weird thing out of first order gradients. We're going to create these vector fields made up of partial gradients, okay, which we cook up these third order polynomials, create this vector field of partial gradients, and then take its divergence. But that thing, because of the structure of the functional, happens to be a measure. Yeah? So that's our substitute for having the gradient of the gradient as a measure. We have the divergence of a vector field made up of the gradient is a measure. Yeah? It's kind of in the same world. Huh? And we have that for two particular vector fields. This guy and this guy. Yeah? That's going to be our substitute for the theory of BV functions. And that was, I think, part of the motivation of this is that the initial people who studied this saw this and thought, hey, we can start to build a kind of structure theory of functions which have the property that when we create these third order polynomial vector fields out of the first order partial derivatives, they are a measure, and we'll have a structure theory which is kind of mimicking the structure theory of functions whose gradient is a measure, and then we'll start to prove the gamma limit in the way the monochrome Motorola function was analyzed. And it's not so easy, but it's a very attractive idea. So this is one of the early results. If you have a sequence which has got bounded Aviles-Giga energy, okay, firstly, the sequence will converge strongly in W13 to some limiting function. And if you create your two measures, mu of u and nu of u, okay, then the absolute value of this measure on your domain will bound below your sequence. Yeah? Will bound the energy of the sequence. And furthermore, if by some fluke it happens that the limiting functional is actually going to be in the space of functions whose gradient is BV, then this crazy measure, its absolute value, is just the jump across the jump set to the power 3. It's just exactly what our example seems to be giving us. Huh? So this crazy measure we've cooked up seems to be exactly the natural limiting energy for a sequence of functions of bounded Aviles-Giga energy. Huh? Okay, but there's no reason that this has to be true. In fact, we construct examples for which it's false. Yeah? Yeah? But if it is true, good things happen. So, what do they not know? Well, at this point, a lot of things we don't know. We have compactness, we have a limiting function space, we have a lower bound. We don't know that the energy is concentrating in any sense on a rectifiable set. That would be the natural conjecture. And that's completely open. But if some fluke, we know it's BV, then it does concentrate on the jump set, and it's exactly what we expect. So, a few more definitions, the last definitions. We're going to define something called an entropy, and it's kind of inspired by conservation laws, hence the name. And it's the following thing. We're going to have some vector field, capital phi from R2 to R2, it's called an entropy, if for every smooth divergence-free vector field M, which has got norm 1, when we calculate the divergence of phi of M, it's equal to 0. Okay? It's a bit of a mouthful, but let's keep it all together for a second. We've already seen these guys. Let's take some third-order polynomial vector field created like this. This is basically our other example, but we flip it around and put a minus sign. And this is our second example, again flipped around with a minus sign. Simple calculation. Let's take a smooth vector field M, whose norm is equal to 1 everywhere, which is divergence-free. And let's create the third-order polynomial with this guy here, capital theta, okay, and calculate the divergence. What you're going to get out is this plus this. Now, since the norm of the vector field is equal to 1, this thing is just canceling out to 0. And since it's divergence-free, this thing is equal to 0 too. Yeah? So this guy we've cooked up here from our previous example is an example of an entropy, almost. It doesn't have compact support, so not strictly. But entropies are things we've seen already. And this other guy, the same calculation, we take the divergence of a divergence-free M plugged into this vector field. It turns out we're going to get this, which is going to be 0 because the norm of the vector field is 1, and this, which is 0 because the divergence is 0. Okay? So entropies we've already met, but it turns out there's lots of them. There's lots and lots of entropies. And again, this was inspired by compensated compactness, where they prove a sufficiently rich class of entropies to get compactness. You can prove characterizations of these sets, and there's actually, of these vector fields, and there's a whole bunch of them. And we just have two examples we've just studied. So those are entropies. Oh, I lied, because I do have one more definition. We let this set A of omega be the set of all essentially bounded vector fields, such that when we create this measure given by the divergence of phi acting on the vector field, for any phi which is an entropy, that thing has to be a measure. Okay? So once again, we talk about vector fields. Okay? We're going to take our entropy, we're going to create this phi of M, and we're going to take its divergence, and we insist that that's a measure for every choice of entropy. Yeah? Okay. It should not be hard to believe that if you take your sequence of functions, un, which has got bounded Aviles-Giga energy, and you take the limiting function u, then u will be in that class. So the limiting function will be a scalar function. So the gradient will be a gradient vector field. We flip it around, we get a divergence-free vector field. Call that guy m. M will be inside that class. Okay? Now, here's a theorem of Deleuze-Zanotto from 13 years ago. For any function inside that class, any vector field inside that class, there exists a one-dimensional set J for jump, which has got finite H1 measure, okay, or theta finite H1 measure. And for H1 almost all points outside it, we have this kind of, they call it vanishing mean oscillation condition. So this is not as good as saying that we've got a Lebesgue point, because this thing is the average of the vector field of a ball of size r, and that average can change. Okay? So this is not as strong as saying we've got a Lebesgue point, but it's some kind of Lebesgue point type condition for H1 almost every point outside the jump. Huh? And on the jump, we have exactly the trace condition that you expect from PV function theory. Okay? So it's getting sort of close to the kind of characterization of BB functions that we want, except they don't know if you have your set J. There could be a set J, or it could be that the measure is just all dispersed. But J is the one-dimensional part, and on the one-dimensional part we have traces, and outside it we have almost a Lebesgue point. So we start to get nice properties of our limiting function space. Very nice theorem.
So J is kind of a jump set, right? But maybe is the property C that seems to work in J and property B.
B and C you have to swap.
Oh, yes, C holds for J, and yes, this should not be a not here. This should be in J, and this should be not in J.
Okay.
Sorry, typo. Thank you for the question, for the correction. Okay, so that's as good as we've got for trying to prove concentration of energy. We've got that there'll be a limiting function. It'll be inside this space. There could be a set of finite, theta finite H1 measure where we have nice stuff, and that could be some part of the energy. But the actual energy could be dispersed all around. There could be all kinds of stuff. It could be a part of dimension between 1 and 2, a so-called Cantor part. It could be an absolutely continuous part. So let me say that a little bit clearer. So we could just create a measure sequence like this, right? This will form a sequence of bounded measures. We could take the limiting measure. Yeah? The limiting measure will be some kind of candidate for the energy. And we'd expect the limiting measure, so this will converge weakly to some mu. Okay, this is too rough, but this is a kind of idea. What we'd like is the mu to be supported in a rectifiable set, and that rectifiable set would be this J. But it could be that mu will have an absolute continuous part or a Cantor part, okay? But actually, that's just rough because these are not the guys. This mu is not the limiting guy. The limiting guy will be these measures we get from the entropies, because we need the cancellation, okay? But think of it this way. Trying to prove that the energy is concentrating in a one-dimensional part. And the one-dimensional part, if it exists, will be nice, but we don't know that it's much on the one-dimensional part. All that stuff is open. There's no more progress on the entire story since 13 years on this question. Okay? So that's the gamma convergence part of the question. So the conjecture is that the limiting function space I gave is the limiting function space of the gamma convergence, and that the energy is the energy I gave. Yeah? All that is completely open. The second main question to do with the Aviles-Giga function is the characterization of the minimizer. And what do we know about this already? So if omega is an ellipse, let's take the distance function away from the boundary. Well, this guy will energetically be as good as the sequence of minimizers as epsilon n goes to 0. So if we take the sequence of minimizers, the energy of those guys will tend towards this. That doesn't mean that for any epsilon n, the minimizer is anything like the distance function away from the boundary. But energetically, it's not doing any better. Okay? So this is an early result of Jin and Cohn. So energetically, we expect the distance function away from the boundary to be the good guy. There's some recent progress by Ignat and Merlet, who might be even here, right? Okay, good to meet you. That similar theorem is true when we have a stadium or when we have a couple of other domains. So union of two circles and some kind of ellipses, then we expect the similar function, a similar theorem is true, except when you have union of two circles or some class of ellipses, it's not exactly the same Aviles-Giga function. It's a slightly different cost function. But for the stadium, I think it's exactly the same. So this is broadening this Jin-Cohn theorem. And Jin-Cohn conjectured that the minimizer is always going to be the distance function away from the boundary when we have a convex domain. It's definitely not true when we don't have a convex domain. Oh. If we take the union of two circles and we set it up correctly, then we can take the distance function away from the boundary, which will have as a jump set like this, or we can just have like a tent coming off like this and a tent coming off like this, and then have the jump set coming out here. And if we set this up right, both of these guys are energetically the same. Okay? So it's not true without the assumption of being a convex domain. But I think we believe it. Well, I certainly believe it if we have a convex domain. So I was working on the trying to prove the energy was minimized. The energy of the Aviles-Giga function was focusing on a one-dimensional part. I was working on the gamma convergence conjecture actually. So, and as a kind of consolation prize, I got some kind of result about what happens when you have low energy solutions of the Aviles-Giga function. So here's the theorem. So it came out in 2014. It was actually online, I think, from 2009. So it took a while to actually come out. But here's the theorem. So we have W22. We have a slightly more general boundary condition. And there exists a positive constant C and a constant less than 1 gamma, such that if you have some function that takes the Aviles-Giga energy to some small amount, to some small quantity, then that small quantity controls how far away your original domain was from being a ball. Okay? So this theorem has no real content unless you have a small energy. Yeah? But if you have a small energy, then that small energy controls how far away you are from having an original domain close to a ball. So the only examples you can construct where the energy is close to 0 are examples where the domain is close to a ball, and this theorem is a kind of a converse. If you do have small energy, then you are close to a ball. And secondly, this says that the gradient of your function minus the gradient of the distance function away from the boundary of the ball is small. So it characterizes the function, it characterizes the domain with a root power, which is definitely suboptimal. The root power is some awful number like 1 over 1,000. So this is well off from what you'd expect as an optimal theorem. But nevertheless, it's some quantitative control of functions of low Aviles-Giga energy under these conditions. So as a corollary, if you have a convex set with C2 boundary, okay, and the curvature is bounded above by epsilon to minus 2, then with this boundary condition, if you take your minimizer will be close to the distance function away from the boundary with some control, which is in terms of how far away the ball was originally, sorry, how far away the domain originally was from the ball, plus epsilon to some root power. Okay? So it's some kind of weak characterization of minimizers for a class of domains that are close to balls. Okay? But yeah, highly suboptimal. After this, well, actually before it, but after it came out, I was thinking about what if you do have a ball? Well, you can do much better. You can get a root power of epsilon. I'm sure you can do even much better than this root power of epsilon, just by much simpler arguments, by some elliptic regularity and kind of following integral curves. You have a fairly short proof of this. Still not a complete characterization, so Camilo and I are thinking about complete characterization, and hopefully we'll have something to announce fairly soon. This was a kind of generalization of a result of Jabin, Otto, and Pertam. So this is my reformulation of their theorem. If you have a bounded domain, okay, which is C2, and you have a sequence epsilon n such that the Aviles-Giga energy of un goes to 0 with respect to this domain, then you'll have a ball as the limit. Then the ball is your domain, and the limiting function is the distance function away from the boundary. So they proved this by a kind of compactness argument, and my theorem was in some sense a quantitative version of that over convex domains, and it uses a lot of the same ideas, this very precise characterization of entropies, which was provided by De Simone, Muller, Cohn, and Otto in some earlier paper, and a bunch of other stuff. So I like this field very much. I was working on this a long time before I had anything to say, and I still like this field very much. And there hasn't been an awful lot. There's been Ignat, Merlot, myself, and I think those are the only papers I've seen recently on this topic. So I'm keen to encourage more progress. But these questions are hard, so I came up with some problems which I think are not so hard, in case anybody's interested. So first problem, prove an analog of my theorem for general C2 domains. I'm sure that's accessible. I'm sure that can be done. Second problem, instead of hitting the full gamma convergence conjecture, what if instead we just proved that outside the jump part, we do have vanishing mean oscillation in the classical sense? Yeah? So we have a true Lebesgue point. And if we did have that, then my guess is that for any curve that we have that doesn't intersect the jump point, then the precise representative will be continuous along that curve. Let's go for that. That's a kind of a nice characterization of our functions we can expect to be true. Problem 3. So we don't know anything about concentrating the energy. So if the energy goes down to 0, then I can say something, and this previous result by Otto, Jabin, and Cohn. What if we have that for every entropy, the limiting function, the measure we get is going to be absolutely continuous? Okay, so we don't have anything about we don't have anything about concentration except it's absolutely continuous. Then can we show that the domain's a ball and we have the distance function away from the boundary? So this too, I expect, is quite a lot easier than proving that there is no part of dimension between 1 and 2. Just give yourself absolutely continuous for every single choice of entropy. Try and characterize it then. And that's another problem I'm working on. I think something can be done. So finally, let me give you a list of references. These are 6 classic papers in the field. These are beautiful papers. If you get into the subject, you will like it very much. So these are the 6 classic papers, and the ideas are kind of all similar and related. They all kind of build up from each other. So if you like this subject and you want to know more, any one of these guys is worth reading. All right, so that's it. Thank you.